Mm. So hello guys, again to another lesson. I see fewer people joined. It's rather futile to ask those that joined why, but just to gauge your feelings about it. Aren't you worried about the first exam? Are you worried about it or not at all? Very much? Well, don't worry guys. I promise you there are going to be very, very interesting problems. Right? So at least one of them, you know, people throw at me their math garbage, and I actually put it on the exam as a revenge. When is it? You will see. You will see. You would have advanced warning about this exam. I do advise you, and I hope that you are not here just because you are studying my class. I mean, what do you care? You will pass this course. It's not a big problem. I'm pretty sure everyone will pass this course with this type of setup. What you do care about is learning this material, learning it really deeply. And for that, you want to solve as many exercises as possible, including the previous two exams. Okay, so there are two exams from prior semesters, and there will be another exam for us that we will submit. Okay, so let's talk about the comprehension check. Okay, so I advise you, you can do, once you're comfortable, you do those Kafka protocols in your head. You don't need to write it out, but definitely on the exam, you show me how you carried out the calculation, your reasoning. Because if I find that there is a mistake, I try to judge, is it a bad mistake or not a bad mistake? And if you just wrote the solution when the solution happens to not be correct, or even if you happen to write the solution, I would like to see what was the process. So for this problem, the sample space that I can pick can be thought of as six numbers from the population cards. All right, so the outcomes of experiments here are going to be cards numbered from 1 to 52. Correct? From 1 to 52. And what I will be instructed to fill in the Kafka form, I have to arrange those items. I sort them in order. In other words, the cards are given to me simultaneously. So the protocol for the full sample space is very simple. I can just have 6 boxes in which the numbers have to be arranged from smallest to largest order. And that represents 52, choose 6 possibilities. You understand why? Because the idea is that you present the subset of size 6 from out of 52 unique elements. And you arrange that subset to present it. You methodically arrange it from smallest value to largest value. Good? Now, the protocol for the 3 pairs that I pick is first of all, the information will be, in other words, if the outcome is success, and success means that I have 3 pairs, 3 pairs, right? So 3 pairs means I want the information that I read here should tell me what 3 pairs I got. And every time I get 3 pairs, I know how to write my answer in the Kafka protocol. So so there are 13, choose 3 possibilities for the pair values. So let's say the pair values are 2, 4, and 11. That's how I put it in order. And then I have this box, those are suits for smallest pair, suit for middle pair, suit for the next pair, right? For the last pair. And so the answer is 13 choose 3 times 4 choose 2 squared. Let's see how many of you wrote the answer. So very good, Shabeli. Excellent, Shotaro. Right, so absolutely correct. And think about, I mean, I might not stop just this moment, but we can discuss wrong solutions. And you see, how do you know, well, when you are worried that the solution is wrong is when you haven't fully visualized exactly how you put this information on your document. Good? That's why I call it the Kafka protocol, is that it's very difficult with probability to be right and be certain that you are right. But yeah, but if you follow this type of procedure, if you can create it for a particular question, then you can be certain that you are correct. And that probability, when you calculate, it's about 0.003. So 3 thousandths, right? 3 thousandths, which happens to be a certain number about the disease that you can, that it's pretty famous right now. That's the probability according to, for example, evit of dying from COVID. The birthday problem. So this you submitted about, I think, 11 or 12 birthdays, and none of them actually. So the problem, the way I wanted to present, was not solved. I do have very few people in this class and very few people that responded out of the class. So here is the question, guys. If n people are present in a room, what is the probability that no two of them celebrate a birthday on the same day? Oh, great, Naomi. I'm very happy. I was thinking I'm missing someone vital, but I could not remember whom, right? Like
Sorry, I had a midterm that ran late.
No worries. You don't have to apologize. I just was thinking, who do I know here and I'm missing? I just felt it, right? So I didn't know, but I felt. So this is the question for which I asked you to submit your birthdays. Naturally, too few submissions resulted in no interesting results. So if n people are present in a room, what is the probability that no two of them celebrate their birthday on the same day? You can calculate it for just n. And of course, it's interesting to know, what do you think, how many people must be in a room for this probability to be less than one half, less than 50%. So Valeria says 30. Are you saying, Valeria, 30 is how old I am? Well, that's nice of you. I'm much older.
No.
Right.
No, I think that I was reading about this problem, and that I think 30 people, you already would have people that have the same day birthday.
Well,
something like this
would have. That's the thing. So we will see below what is the number and when, right? We will see how to estimate it. Hopefully you would like the estimate. The estimate will be something that you remember from our review. Okay. So for now, guys, what I want you to try to do is just calculate how many people, just calculate, if you have n people, what's the probability that no two of them celebrate their birthday on the same day. Well, for Shotora, be careful, right? That's what I mean when you don't have a protocol. Okay. When you already type the solution, or let me know when to proceed. No worries, guys. So when you're, it's okay. I'm glad that you make it at any time. Yeah, I wonder if you were taking the same test together, Gabriel. It's nice to do things in group. Well, Shotaro, still you have to think about the document. That's what I mean Kafka document. It's never right until it's documented to be right. Bureaucracy is very important for probability. You see what you did, Shotaro? You numerator you have an ordered collection of birthdays, in the denominator you have ordered birthdays. First person, second person, third person, so I suspect. And guys, right, so another wonderful thing is you have office hours. You know, you can talk to me. Even though I'm strange, but some people actually, when they have complicated questions, they love talking to me. Only then. Over the weekend, you know, somebody said, oh, I have this problem from previous semester in combinatorics, which is now another extra credit for you. Old students give me hard problems to then reassign to you. That's the nicer cat. if you're interested. All right, so let's, I guess, discuss this problem together. It's pretty interesting. You will see why. So how many ways to assign those birthdays? So imagine we have people that they are wearing a tag 1, 2, 3, all the way to tag number n. And the first person could have been born on any of the 365 days. The next person, if the next person, person number 2, doesn't have the same birthday, there are only 364 options, yes? And all the way to the last person, it's 365 minus n plus 1. Because, you know, it's 0 all the way to n minus 1 that we have here, right? I did not draw the document, but you can imagine what it is. It's just a box for person 1, box for person 2, and each next box has fewer possibilities exactly by 1 integer. So it is this number, yes? Also, you could have written this number the following way. I mean, right, I would have said you could have written it as 365 choose n, because you need to choose n birthdays, and multiply it by n factorial, because once you choose the, let's say, well, Shotaro, you roll 365 choose n, so that just means the particular birthdays we get. But if we assume person 1 birthday, person 2 birthday, so we need to not just know the birthdays, we need to know which birthday belongs to which particular person, correct? That's the way we decided to have this problem. You can figure out, unless you have a different denominator, right? So then you have 365 to the power of n, because in the denominator, the first birthday does not affect the next person's birthday, and etc. So both of those answers are correct. Good? Wonderful. Now, here is the interesting fact, right? And if n is bigger than or equal to 23, this probability is less than 1/2, which means that if you have 23 students or more in a class, then the probability that at least 2 of them share a birthday is bigger than 50%. Now, how can you see that? You can clearly see that by just plugging in the n, but then you have all those ugly calculations. You can do the following process, okay? So imagine that we are conducting a bunch of experiments, and in the experiment will be of the form kj, where I compare person k with person j. I compare person 1 to person 2, person 1 to person 3, person 1 to person 4, and all of them. I have a combination of every possible 2 individuals, and I try to verify whether or not those 2 individuals have the same birthday. By restricting sample space, it's pretty clear that the probability that they have the same birthday is if it's just 2 people at a time, 365 squared is the sample space, right? 365 for guy number 1, 365 days for guy number 2. And to share a birthday, it's either on day 1 or day 2 or day 365. So the probability that 2 random people share a birthday is 1 over 365, correct? And therefore the probability that they do not share a birthday is 1 minus 1 over 365. Agreed? It's 1 minus that. It's pretty important. So how many possibilities, how many combinations of pairs of people? If we have n people, there are n choose 2 pairings of those people. Do you agree? Yeah, so ask me a question, guys, right? I might be saying something fast, and if I'm saying it too fast, just talk to me. You understand why there are n choose 2 people, right? So if I have, let's say, 5 people, I have combination 1 and 2, 1 and 3, 1 and 4, 1 and 5, 2 and 3, 2 and 4, 2 and 5, and onwards, right? I can compare them like this, and that's the same as n choose 2 possibilities, because notice when I say 1 and 2, 1 and 3, I give the presentation of a subset of size 2 out of 5, where the first element is smaller than the next element. The number on the first person is smaller than the number on the second person I compared him to. So it's n choose 2. Now I will explain why multiplication probability works. That will be the next chapter, right? And how does it work, right? So for now, you can see that the probability that there are no matches, it's not exactly true. It's approximately probability no match on first trial, second trial, all the way to n choose 2 trials. It's approximately this number, kind of like this. You see, here is the diagram. There are how many comparisons? In my experiment, I have n people, but that creates n choose 2 possible matches. Make sense? So no success. In other words, no same birthday on trial number 1, trial number 2, all the way to trial number n choose 2, and each of them is 1 minus 1 over 365. Now, how do you multiply and when do you multiply? That's the that will be the discussion in chapter 3 when we talk about conditional probability. So I'm skipping a little bit to show you ahead of time what this is, what this looks like. Make sense? So it's not true that I need to just multiply those probabilities because they are not exactly independent, but the result is very close to true. And so the number that I get is 1 minus 1 over 365 times n minus 1 over 2. What does this number look like? Any ideas? What does it look like? So if you studied calculus pretty well, then this number looks to you like light bulbs go on. It looks to you like something. Yes, Kazi. Exponential growth, and we talked about it. So exactly here is roughly the probability. Probability that there are no matches is approximately 1 minus 1 over 365 to the power of n choose 2. This is just n choose 2 here. Yes? Now, here I think 1 minus 1 over a large number. And I think what number do I want to put on the power? I want it to be 365 because what I have now in the square brackets looks like what number? This in the square brackets looks like the number e to the minus 1. Do you see that? We spoke about special sequences. This looks like e to the minus 1. So, and then if I multiply by 365, I must also divide by same number. I must divide by the same number. So I have e to the minus 1 to the power of n minus 1 over 720. Okay. So then I can use this estimate to figure something interesting. So the probability the probability that it's less than some number p, the probability that if I have enough people, this number is less than p, is what I put in this red box. Good. Now I can solve this inequality using logarithms. I just take logarithms of both sides, and I have minus n minus 1 over 720 less than ln of p. And this reduces to a quadratic equation. Here is the quadratic equation, which when you solve it, you realize that n, because it's a positive integer, has to be bigger than or equal to the expression on the right. You can just yourself try that at home, see if you have this expression. And now all you do is you plug in p. So if you want p to be 1/2, plug in 1/2 here. And what you get is that n is bigger than 22.999, or n is equal to 23, because it's the integer directly bigger than the quantity we get. Okay. So suppose that I want the probability that there will be a match to be 90%. In other words, probability that no person shares a birthday with another person to be 0.1. So if it's that, if I plug instead of p 1 over 10, I will get that my integer n should be bigger than 41.5 something. So I'm assured that if n is 42 people, if I have 42 people in my class, the probability that they share a birthday, at least 2 people share a birthday, is over 90%. It's almost certain. Is it interesting? So you understood, guys, here E came to play a role. Unfortunately, in our class, based on this calculation, in our class, if everybody submitted it, I think we have, 17 people in the class, the probability of success with 17 I will try this after COVID, Kazi. How do you mean? COVID doesn't seem to be over, definitely not before the elections. So yes, well, it can be held again now. It's just up to you if you hold it. So what you have is that if the number of people that you have in a party is 42 people or more, it's 90% certain that at least two of them share a birthday. And you know, I did this experiments with students in class when the class is bigger. In our class, I estimated the probability to have been I think 23% if everybody replied, but naturally not everybody replied, so it was lower. Right? You cannot make students reply aside. So here is the next question, guys. I hope you will find this question fascinating. I cannot always tell if I don't see your face. So we have a deck of 52 cards. They are shuffled. Cards turned up one at a time until the first ace appears. Is the next card, the one after the first ace, more likely to be the ace of spades or the two of clubs? I would like you to think about it and let me know. What do you consider? Do you understand the question, right? So we shuffle the deck of cards, and I'm going to turn cards one by one until I see my first ace. And then I ask you, what do you think the next card? Do you prefer to bet it's the two of clubs, or do you prefer to bet that it's the ace of spades? You understand? And naturally, I mean, you have to understand that I'm asking this question before the experiment is run, right? You have to answer this before you see what will happen. What do you prefer to bet? Because naturally, if you see that the first card is the ace of spades, you're not going to bet that the next one will be an ace of spades, correct? So the idea is that you place your bets before the cards are upturned. So Bowen says equal probability because they are independent events. By the way, Bowen, yes, you made the mistake of telling me that you know Russian, so I do want to see how well. Let's say can you answer those questions in Russian? That would be one way for me to judge it. Then we need to work with you, right? I need to show you some inspirational videos. Oh, interesting. So Nomi says both are 51 factorial over 52 factorial. What the rest of you think? Maybe you are, well, I want to see what the rest of you think before I say anything more. My little bureaucrats. Okay, Kazi says he thinks it's two of clubs. Sandy agrees with Naomi. And Paulina agrees with Naomi. Paul. You see why I called you Paulina? Because I figured right away you are a character from the player if you started reading it. Dostoevsky's player. There is one person I haven't heard from. What about let's see? What does Chabeli think? And who else is here? Did somebody escape from me? Oh yeah, Melissa, and of course, obviously, I want to know what you think. Wow, Melissa, interesting. Oh my God. I'm so proud of you guys. Right? So very proud of you, my little soulless bureaucrats. You already have no feelings, right? And you know how to figure it out just because you can put a document. Exactly. You're absolutely correct. They are equal. And now, why are they equal? You see, here is how you can figure it out. So, if the cards are arranged randomly, there are 52 factorial arrangements. Yes? Now, how many arrangements correspond to the ace of spades being the second card? What I would have done, but the way I think of it, actually, here I prefer to not think of a document. I prefer to think of taking a card out, that ace of spades, taking it out and shuffling the remaining cards, right? So then, and the ace of spades must be then somehow placed right after, I think it was the ace of spades, after the first ace. You understand? Shuffle the cards, the ace of spades is second. So in other words, it's like the ace of spades is glued, is glued afterwards to the next card, to the, previous card, to the previous ace. And so you have 51 factorial arrangements. You understand? Once you arrange the other cards among themselves, the ace of spades must, its position must be determined for the successful outcome. You understand? All you are doing is this combinatorial problem where you count how many ways can success occur. And if success occurs, that's what you have to understand. If success occurs, it's just arrangements of the other remaining cards other than the ace of spades must be provided, because the ace of spades, its position is then determined to be the next card. Make sense? So as soon as I know all my cards in my information on all the cards, the aces maybe are written in red numbers, for example, right? And then those red numbers, the first red number must be followed by the ace of spades, so it's determined. So it is 51 factorial over 52 factorial, as Naomi said. And there is absolutely no different calculation when you use the two of clubs. You just now you just take out the two of clubs. As soon as you know information about the remaining cards, the position of 2 is determined for the success. So there are 51 factorial possibilities where 2 of clubs is the second card. The probabilities are exactly equal. Makes sense, yes? So I think it made sense to quite a lot of you. I'm very happy. The only problem, magic is gone, right? I mean, how could it be or what? Yeah, you don't care how could it be. Just a pure cold calculation. All right, so next problem, somewhat, well, of course, it's all of them are trick questions, right? The trick is not to be tricked. Yes, like Leibniz, but in essence, you understand when you play probability, there is another thing that makes me wonder. You see, probability is based on the limit. It's just outcomes based on habit. Right? But what if you go and play the roulette once in your life? You're not going to repeat it. You just go and maybe you have fool's luck, what you call it. Right? That does not violate probability, right? The probability is saying that if you make a habit out of something, then that number is going to come out. But if you throw a coin once, what does it say? So you have those types of thoughts that to me are problematic, at least. So 20 offensive and 20 defensive players in a football team, they are going to share rooms. They are going to be roommates, 2 of them at a time. You understand? So you will divide them in pairs, and they will go into their hotel rooms. So problem A, what's the probability that no offensive defensive roommates pairs are made? They're made at random, of course, right? So just you sample them randomly then. How are we progressing, guys? Getting well? Well, Naomi, 40 choose 2, 2, 2. That is the what?
I mean, I did 40 because there's 40 people,
Yes.
and then you're splitting them up into groups of 2.
Mm-hmm.
So it would be like 40 choose 2, and then 2, and then 2, and then 2.
Right. And that is what? In other words, because it's a probability question. So here you're calculating what specifically?
I guess the number of pairs you could have.
Almost, right? So this is the
Kind of.
number of pairs with room assignments. Because that means what? That means that we have our knights and our dragons. The knights are the football players. Makes sense. What are the dragons?
The rooms.
Exactly. Right. So this you can work with the sample space. Just be extremely careful. Yes, we have knights, dragons, but then in this group we are not. This is not the pairings, right? This is just the rooms. So those are pairings aside to rooms.
That what you meant?
Very okay. So interesting, right? Good. So that's correct, right? We can rearrange those in 20 factorial ways, Naomi. Is there ambient noise coming through the speaker or no disturbance from my end? Good. Right, welcome back, Melissa. We are solving this example. Yes, Naomi, that's just the sample space. Now we want the probability that there are no complete offensive defensive pairs, no pairs like that. Oh, great. Let's see what we have there. Then the numerator would be 20 choose blah, blah, blah. Yes, very nice. All right. So shall we go ahead and do it, guys, or you still want to work a little bit longer on it? I don't mind, right? It will be a fewer notes to write for Wednesday. I have lectures prepared for a little bit, but I'm not sure if to occupy the entire Wednesday. Okay. Okay, Shotaro, good. Well then, shall we go through the example together, guys? Oh, it was nice, right? You worked like this. It was very pleasant. So here is my document. You don't always have for yourself, in your mind. In my mind, I'm not writing this out. I see it in my mind's eye, right? But it will be very nice if you do it on my exam naturally. Right? Then I see that you understood how I am doing it. You can also indicate it in other ways. So first of all, I think of the Kafka protocol for the sample space. So I first imagine that the paper given to me has room 1, room 2, all the way to room 20, because there are 40 individuals. You divide them by 2, and that's how you know how many rooms you have. Good. So initially, the rooms are like the dragons. You see, here is I have the players ranked by population number, and I place a small number, a bigger number like this, right? And that's the room divider. So this tells me that there are 40, choose 2, 2, 2, 2. Possibilities of filling this document, where the rooms are the dragons and the players are my knights. So there are initially 40 factorial divided by 2 to the power of 20 possibilities of filling this information out. Good? Now, because then I see that actually I don't know anything about the rooms, I cross it out. Agreed? I cross it out. There are no room information. I don't know who goes where. So let's say if I have the numbers 1, 2 here and 3, 4 here, that's the same that if I place 3, 4 here and 1, 2 there. It's no difference. Because I can move the pairs. You understand? This means this pair goes to room 1 and this pair goes to room 2, and this means the opposite. This pair goes to room 1 and this goes to room 2. But in terms of pairs, that nothing changed. The pair assignment stays the same. Correct? So that's why I divide by 20 factorial once I cross it out. So now let's consider the document for part A. Here is the document that I imagine. So we have offensive document and defensive document here. And initially I have offensive room 1, offensive room 2, etc. 10 rooms for the offensive team, and defensive teams, there are 10 rooms. So without crossing anything out, we have here we have 20 choose 2 to 2 possibilities, right? 20 choose 2 to 2 possibilities for this assignment, and 20 choose 2 to possibilities for the other assignment. But then I crossed out those rooms, so that means here I divide by 10 factorial, and here I also divide by 10 factorial. Here I made it blue and red so you can see it. So altogether, what is this? This is 20 factorial divided by 2 to the power of 10, and this is the same, so it's 20 factorial divided by 2 to the power of 20, and there is 10 factorial here because we crossed out those rooms. Make sense? So you see, I visualize it very quickly, and because once you practice enough of it, you get see the answer very fast, either by writing it out first or by having it in your mind. Good. So that's my numerator, and then I just take numerator by denominator, and I get this number. It's 1.34. Basically, it's about 1.5 of a millionth, right? It's very small probability of this happening if we are doing it random. And maybe, of course, there is a better solution, but definitely I know the solution is correct. You understand? So when you can model the sample space and you can model the desired outcomes in that sample space, then I can be sure that my answer is correct. If you do it another way, you have to also try to figure out why you are sure that it's the right way. So now let's carry out B. Now we are assuming we have 2K pairs, 2K offensive and defensive pairs. So what must we do? We must pick 2K offensive people, 2K defensive people, and that means 20. I did not write the document because, you can imagine it, right? So even when I write it like this, that indicates a document. That means that I'm listing first which defensive people were picked, which offensive people were picked, and then I order them. Basically, I imagine that that once I order them, then I have the defensive people on the top and offensive people on the bottom. So they are going to be 20 choose 2K, 20 choose 2K times 2K factorial. You understand why that is the case? And then for the remaining people, they are not supposed to be together. So I do the same procedure as I carried in part A. So this is the same procedure, except I removed 2K individuals. So this part is part A, but with fewer individuals. Make sense? And the denominator is, of course, still the same thing as it used to be. So you understood how I was tired. I didn't write you the Kafka protocol. Do you see the Kafka protocol from this line? So what this means is this. So first I have offensive. So let's say defensive, then offensive, and then the 2K factorial means this. I now reassign. So once I pick my pairs, I assign them numbers. I assign red numbers 1 through 2K, and blue numbers 1 through 2K, and then I just juxtapose, right? I have each defensive player stand by himself, and I adjoin below him the other type of player. Make sense? So this concludes today's lecture. Next lecture will involve infinite series, and with that we will finish chapter 2 and begin chapter 3. Please, if you have questions, I'm sure you should have solved quite a lot of problems from chapter 1 and chapter 2 already from the book, so we can talk about those questions if you were stuck or you want to run by me your conclusion. Then take care, guys, if you're not staying, and if you are, then remain here.